I'm going to take you through the underpinnings of section 10.1. We're going to follow pretty closely just through what you see in the notes, the outline pattern that you have here. And what we're going to focus on this session is we're going to look at two random variables. We're going to assume that they are independent random variables, very important point. And in this unit, we're going to look at the difference between the proportions, two proportions, categorical variables are what we might have underneath. So we're going to look at, the proportion of successes, the proportion of people who want to vote for a candidate, so on and so forth. And we are going to compare two proportions. We're going to do it with confidence intervals. We're going to do it with hypothesis testing. So again, this is section 10.1, and we're going to follow through essentially all the bullet points that you see here. They might not all be talked to explicitly. They're certainly in the textbook. We're going to hit most of them pretty well as we work through this. So as we get started, there's a couple things I want you to recall. This is from way back when in our earlier chapters. Two independent variables, x and y. The mean of the difference of two random variables is nothing more than the difference of the two individual means. The variance of one random variable minus another, again, independence is key here, is nothing more than the sum of the variances. What's that mean? Well, a standard deviation of the difference between two random variables is, you can see this, variance minus variance, no problem. But what's it come down to when we get all said and done is the standard deviation of the difference between two independent random variables is nothing more than the square root of the sum of their variances. So this is kind of our key takeaway here, and we're going to use this over and over. Now also, from chapter 9 in particular, and work that we've done in that chapter with in 8 and 9 with confidence intervals and hypothesis testing, remember, a confidence interval for our proportion is our sample proportion plus or minus a z-value, depending on our confidence level, times the standard error, the standard deviation of the sampling distribution, which in our case will be our p hat times 1 minus p hat over n, all of that square rooted. And that turns into, then we'll say we are X%, usually 95% confident that this lovely little interval contains our true population parameter. Now, when we're working with hypothesis testing, we're typically doing something along the lines of we're assuming that our population proportion is P naught. That's what we'll set. That's our hypothesis. That's our null hypothesis. And our alternate hypothesis will be one of either the one-sided, greater than, less than, or the two-sided, P not equal to P0. But how did we test these? Well, again, we can use a z-value, and we actually compute a z-value as follows. It will be our p-value that we get from our sample size n, p hat minus the value that we put in the null hypothesis, p naught, divided by, well, the standard deviation. We're going to assume we work with the thought that the null hypothesis is true, which would mean that the sampling distribution, the standard deviation would be nothing more than p naught, the null hypothesis value, times 1 minus p naught over n, and again a square root. Well, then subsequently for this z-value, we'll compute a associated p-value using normal CDF. And if our p-value is greater than our alpha level, we will fail to reject the null hypothesis. If our p-value is less than the alpha level of our hypothesis test, we'll go ahead and reject the null hypothesis. So that's all background. Let's get into the gist of what do we have when we're working with the difference of two proportions. Again, remember, independence will exist, and all the conditions of all of the conditions that we've talked about from before, we're usually going to look at. We want to make sure that we have simple random samples. We're going to assume that we have a large counts condition that allows us to assume that we match our sampling with replacement will look like sampling without replacement. And finally, what else will we look at? We'll go ahead with the fact that we will meet the 10% condition as well. Now, we'll have two populations. First thing that we look at in Gauner proportion, the second thing we look at, the second population we look at, we'll just call them populations 1 and 2. Our parameters will be our proportion, our population proportions, P1 for population 1, P sub 2 for population 2. Our sample statistic is P hat sub 1, P hat sub 2. our sample sizes will be N1, N sub 2. Now, what do we know? Well, the individual populations both will, assuming we've met all our lovely conditions that we've done time and time again, then our sampling distribution for the first sample proportion from the population number 1, from that first group, is normal with a mean of the population parameter value, and then a standard deviation of what we know before, p sub 1 times 1 minus p sub 1 over n sub 1. And that same concept will apply to be true for our sample taken from the population 2. Mean will be whatever we assume the population proportion is, and then what? Population proportion 1 minus population proportion divided by the sample size and all the square root of that. That'll tell us, and again, because we've met the conditions, that both of these parameters will be normal with the, or approximately normal, better way to say it, with these appropriate parameters wrapped around it. And so if we have two normal populations, what does that therefore allow us to do? It allows us to say that the difference of the two proportions will in turn be normal with a mean of P1 minus P2 and a standard deviation, which is just what we see when we combine random variables, whether we're adding them or subtracting them. We always add the variances. In this case, our standard deviation will look exactly like what you see here. What does that in turn lead us into? Well, it leads us into the following statement. Our confidence interval for the difference of two proportions will be nothing more than our p hat sub 1 minus p hat sub 2 plus or minus our appropriate z value, depending on what? On the confidence level that we'll be working at, multiplied by the standard error of the sampling proportion of p hat sub 1 minus p hat sub 2, and that's that nice little complicated animal that you see right there. Let's go to town and let's go ahead now and work an example and see all these pieces come into play. And what I'm going to do, I'm going to work off of example 1 that you see here. I'm going to have to just go ahead and put that away just so we don't have too many papers flying around. But I'm going to be working from example number 1 from our note set. And here comes that setup. I've identified our two different groups, teens and adults. Remember, we're looking for the proportion of teens minus the proportion of adults, what the difference between those two populations proportions is. I have a p hat for teens of 0.8 and a sample size of 799. For adults, I have a p hat, notice p hat sub 2, of 69%. Sample size is 2253. Now, how do I run this? Well, what do I know? The sampling distribution of p hat sub 1 minus p hat sub 2 should be normal with a mean of 0.8 minus 0.69 equals 0.11. And the standard error of p hat sub 1 minus p hat sub 2, and I just wrote it again one more time, as a sigma of p hat sub 1 minus p hat sub 2. I just went ahead and plugged in those lovely numbers that we had from our earlier confidence level statement. So what did I do? 0.80 times 1 minus 0.80, 0.2 over 799. And look what my second term, remember, variances add, standard deviations will add the squares and take the square root of such. What do I have here? 0.69, 1 minus 0.69, 0.31, divided by n sub 2, 2253. And when I calculate that, I'll have 0.0172 if I take it out to 3 decimal points. I've been asked for a 95% confidence level. What's that mean? Well, 95% of the data, so to speak, that's where I'd be looking for it to kind of fit. That's where I hope my interval works with. And so what's my z-value? I'm going to run an inverse normal of 0.975 and come back with 1.96. What's that therefore tell us that our confidence interval is? It's 0.11 plus or minus, there's my z-value, 1.96, times my sampling distribution standard error. There's the 0.0172. And if I run those numbers, I come back with an interval that runs from 0.0763 all the way up to 0.1437. Or if I want to, I can say 7.63% to 14.37%. What's my normal statement? I can say I'm 95% confident that the interval from 0.0763 to 0.0143 captures the true value of the difference of the proportion of teens and proportion of adults using social media. Proportion teen minus proportion adults. And that's what our confidence interval gets us in this. One quick aside, notice the following. 0 isn't in here. Think about that. If you were doing a hypothesis test that the proportions were the same, look at what your confidence interval happens to be. It's all greater than 0. This is certainly something that would make you think. Remember what we did with some hypothesis tests and how we compared contents of confidence intervals. When I look at this confidence interval, I think it gives me a lot of ammunition to say that no, there's no way that the proportion of teens and adults would be the same. So just kind of an extra food of thought, just one extra piece of analysis here. The key thing for this stage is really just the confidence interval. So we'll break up our video here. This will cover the first part of section 10.1. We'll roll into our second video to go ahead and consider hypothesis testing for the difference of two sample proportions.